So normally in industry and also in residential applications, we usually have at least two voltages available, right? We're going to have one low voltage, and normally we have 120 volts AC, because there's a lot of stuff designed around 120 volts, because this is why we have this in commercial applications. We have this voltage available in residential applications, and we have this voltage available in industrial applications, right? Okay. I mean, to be awful, you went to U.S. Steel and you couldn't charge your cell phone, right? So 120 volts is out there at U.S. Steel, because this is the predominant voltage that we use. And then above this, we got at least one high voltage. Okay. Of course, in our residential, it's 240 volts AC. And of course, these are what NEC, the National Electrical Code, refers to as optimum volts. At your house, you probably won't have exactly that, right? You understand? You might have, you might have 110. In fact, a lot of people call it 110. If you look at your light bulbs, they're usually rated at 115 volts. Incandescent light bulbs are rated at 115 volts. So this is kind of, so they can't say, they don't always come out and give you the range. I think it's plus or minus 10% we have on these voltages. Whatever this voltage is at your house, this voltage right here will be one half of that. Okay. So we normally have a low voltage, what they consider to be low voltage, and we have a higher voltage. And what advantage does a low voltage have? Yeah, safety. And then what advantage does a high voltage have? What advantage does a high voltage have? But there you go, less current for the power. Now, less current for the power gives us a result of, the results of this is smaller components, right? You understand that? And running more devices, that's an arbitrary thing. So y'all understand what I'm saying? So the advantage is not smaller devices. The advantage is less current to deliver that power, right? That's the advantage. And then the results of that is that we can use smaller components and to carry the current. Now, normally what we do, and to build, not to run, you understand. It's less costly to build, but it's not more efficient to run, because 2,300 watts is 2,300 watts. Y'all understand that? And you don't pay for voltage. You don't pay for current. What do you pay? What bill do we call that we pay every month? We pay the power bill. Okay? And then all your devices in your house are designed to run at a certain voltage. So if you take your dishwasher, which is probably, if you got one of those, it's designed to run off 120 volts, and you decided to wire it up to 240, what's going to happen is you turn it on. All the electronics in there is going to burn up, right? If you got that, everything's going to burn up, because it's going to try to consume 4 times the power than what it was designed to do, right? And of course, if you have a device designed to run on 240, and all you got is 120, and you decide you're going to rewire it, right? I mean, you got 2 wires coming out of there and a ground, but in 240, the 2 wires are hot. In 120, one is hot and one's what we call neutral. So what would happen? Well, it's going to try to produce a quarter of the power, and it's not going to do any work for you, right? So loads are designed to run at a certain voltage, but they're designed to deliver so many watts at that voltage. And then, of course, the higher the wattage, since I is equal to P over V. Now, if it's on the bottom, we call it inversely proportional, right? Understand over here. What do I mean by inversely proportional? Well, if voltage goes up, it means what's on the left-hand side goes what? Down by exactly the same amount. So if I double the voltage, the current's going to be 1/2. Okay, y'all understand that? Now, normally what we do is we put an overcurrent protection device in here, and this is a symbol for a fuse, that little squiggly line. It's not the symbol for an overload. The symbol for an overload is an overload heater. We need to get that out of the way. Is this C, or this hook, right? So this is a symbol of an overload. Overload heater. So normally on single phase systems, low voltage single phase, we only fuse one side, because this side right here is referenced to ground anyway, right? Don't understand what I'm saying? In your panel box, it carries current, but there's no potential that if you got between ground and the neutral in your power system on your low voltage side, you wouldn't get hurt at all. If your ground was correct. If your ground was screwed up, you could. Now, when we get into high voltage single phase, this is where we get in a problem, because high voltage single phase, we don't use a neutral. Both sides are hot. What we call electrically hot, right? Y'all understand that term now. So when I say hot, most of the time I don't mean it's hot to the touch. I mean it's electrically hot. So what we should do is fuse both sides, or put our circuit breaker in both sides. So that's why if you got a circuit breaker panel in your house, you look at the you look at the low voltage breakers, there's only one of them, right? You look at the high voltage breakers, there's two of them. Now they're ganged together. Okay, y'all understand? They're ganged together, and why do they have to do it? Because both sides are hot. Everybody understand that? And then, of course, three phases, all of them hot in relative to each other. So three phases, we would have to put an overcurrent protection device or a fuse in all three phases. Okay. Well, this is single phase. I'm gonna put this is single phase. This is single phase, but this is single phase low. This is single phase low voltage. This is single phase high voltage. What do you mean? No, this is single phase, three phase. This is not single phase. I'm sorry. This is three. Thank you. This is three phase, and all wires are hot relative to the other. Y'all understand? Okay. And most of the time, by the way, when they switch high voltage, and you got to be careful for this, because there's a lot of things that we do in residential that we don't do in commercial, and we don't do in industry. One of the bad things is that we run, and you got to be careful with this if you work on outdoor air conditioning systems. So we got this big old compressor motor out here, and it's single phase. And then we run up here to our control relay. And what they normally do is just they switch one side, and then the other side goes through. Okay. Now, in industry, then, if you're under OSHA, you would find this. Okay. But in residential, most of the time, what you're going to do is you're going to find this. And this is my motor on my compressor. It's also, okay, and I think I passed this relay around where they only switch one side. Well, by George, you better pull the disconnect on this thing, because this voltage right here, if this right here is open, the motor's not going to run because it don't have a complete path. But this line right here is still going to be electrically hot even when the motor's turned off, because this voltage is going to go through the windings in the motor, and it's going to be sitting right there. So there's going to be 240 volts on both leads of the motor even when the motor's not running. Okay, y'all understand? Yeah, right here. I mean, so you're gonna have 240 volts right here, and you're gonna have 240 volts right there, but the motor's not gonna run because the contacts run. Now, where the voltage is coming through, it's coming through the motor coils, and since there's no current flow because the motor's not running, the only way we get voltage drop, voltage drop is equal to I times R. Y'all understand that? Or I times ohms. Well, if I is equal to 0, you know, I could come over here and put 1 gigohm, but 0 times 0 is still what? I mean, anything times 0. So that means this voltage, that voltage is going to be sitting right there. Y'all understand that? 240 volts. So that sucker right there, if you don't pull that disconnect and you're out there working on your compressor, just because that compressor is not running doesn't mean you're not going to get your buttons out, right? You understand? So you got there and run, you got to pull that, you got to pull the disconnect. Make sure you pull the disconnect. Yeah, I think I showed y'all. This is actually a residential relay. Now the coil is 26 volts. Y'all understand now that the coil and the relay doesn't have to be the same, right? So this is actually the relay. Or the contactor that runs a compressor motor on an air conditioning system. And what you'll notice is that one side comes straight through. And I'll pass this around as you look at it again. Manual motor starters, and we got these guys all over the place. The advantage, anytime I start adding automation, and what does automation mean? About unit assistance, right? Maybe we have to get it started, and something might not be fully automated, but we can add automation. So anything that's done all by manual contactors, over the long run, these are going to be cheaper, right? So we run into a lot of these manual motor starters out there. And, of course, we know what a contactor, and they basically ignore the control relay. So normally we have contactors, we have control relays, we have contactors, and we have motor starters. Are we okay? Solenoid action, we've already talked about this. What type of diagram? So down at the bottom, this is a line diagram, and then this is a wiring diagram. You understand the difference? Now, as far as trying to figure out how the circuit works, which one's easier to use? Line diagram, right? And then the wiring diagram tries to show you the physical orientation between the devices. It basically uses the same symbols, but instead of it being drawn logically how the circuit operates, it's drawn to give us a reference of basically how these guys are physically oriented to each other, right? I don't know what figure this is, but we're working inside Chapter 9, even though even though my thing at the top is Chapter 8, this is Chapter 9. These PowerPoints was made out of another version of this book. And we have the same thing here. So we have a wiring diagram here, which I know that these two push buttons here the two push buttons are inside the same unit, right? Because they have that symbol that we talked about where we use long lines and dots and dashes, I guess you'd say. And then I know this relay is located somewhere out here pretty close to phase 2, right? And then these are the contacts being controlled by that relay. But if I try to figure this circuit out, it's pretty complicated. Y'all see that? When actually the logic circuit looks like this. So this is a symbol for a circuit breaker. Of course, this is a symbol for normally closed push button, normally closed. This is a symbol for normally open. This is a symbol for a normally open contact, right? And this is a symbol for a coil, but it's not a motor starter. And why do I know it's not a motor starter? Exactly right. There's no overload contacts on the L2 side. You know, here, Heath. So there's no overloads on the other side. There's only one thing that's allowed between the load and L2, and these are overload contacts. So we have the overload heaters that are up in the motor circuit, right? You understand? But the contacts are going to be in our control circuit. Are we okay? Any questions? And of course, this is not a motor. This is just a three-phase heating element out there. So a three-phase heating element, that's nothing but resistors. And resistors, the current they run on is the current they start on, right? You understand what I'm saying? Where motors, they start with more current than they run with. Are we okay? Yes or no? Same circuit. So this is the symbol for a selector switch. We see a lot of these in And this one, and we see this a lot where we can wire the switch two different ways. We can wire it as a normally closed switch, or we can wire it as a normally open switch. Okay. And this is a two position, and they call it off and on. So what this is telling us, notice the dash line right here on the off side, and then the solid line on the on side. But what they're telling us is if I turn it on, then the solid contact will be made. If I flip it to the off position, then the bottom contact will be made. Does that make sense? Now there's another symbol, and that's what I'm doing here that's gonna bring this up, because the more we work in the class, the more we're going to ask questions about that U.S. Steel print that hopefully I gave y'all 2 copies of it, so hopefully you got that. If you're not, I think it's available in the handout section up there. And so I'm looking down in line. If you got your print, you can pull it out. I'm looking at line 20 and 22. By the way, 20 and 22. Now I'm dropping the 137 because that's the page number, right? And we're supposed to turn in labs 2 and 3 at home. Let's do this Monday, right? Make sure y'all remember that, because I sent out an email and I posted it as an announcement. What I'm looking at is I'm looking at this guy right here. So we're looking at lines 20 and 22. I think I got a couple up here that just got left on the table. That's all I got. Here you go. You don't have it. Well, here's the okay. What we're looking at lines 20 and 22. Everybody understand that? So we got several things that's on, and this is almost directly out of the textbook. The way they teach, the way things are laid out. And the only thing that we don't have on here is manufacturer numbers, which is what y'all supposed to be putting on y'all's diagram. Is that over here on the left we have what we call line numbers, right? And now I can tell y'all where to go. I can say go to line 20, go to line 22, and that kind of stuff, right? And then these numbers right here, these are wire numbers. What did you say that was, Jeff? I ain't got to yet. Good question. And these are what we refer to as numerical cross-reference numbers. Now, what we have here is that this is a selector switch, but this is another way that's drawn it. And can y'all figure this out? Notice here it says forward, and then it's got this little asterisk right there. And then over here it says reversed, and it's got the little asterisk down at the other place. And y'all know what a selector switch looks like, right? Showed y'all several times. Got a knob on it, you turn, and it's got different. The selector switch we have is a 3-position. This would be a 2-position selector switch. Now, the way it works, these are the contacts that are being controlled by the selector switch. So if we put it in forward, it says this contact is going to be closed, If I switch it to reverse, this contact will open and then the bottom contact will close. You understand that? And this is just another symbol for a selector switch. This one here you see used a lot because it's a lot easier to draw for a craftsman to draw. Are we okay? Yes. Yeah, and the bottom will be open. So if I put it in forward, see here's forward for number 5 bridle. And then if I put it on forward, can you see the asterisk right here, Wilbur? Okay, so it means the contact in this line is going to close, which will be this contact. No, on forward, the top contact is going to close. And then on reverse, and the bottom contact will be open. So I'll say 20 will close, and that's line 20, and 22 will open. And then when I put it in the reverse position, then 22 will close, and then 20 will open. And one of them's called jog reverse. Okay, and what's jog? When we jog a motor, what does that mean? Switching it on and off. So it's not starting it up, it's switching it on and off. Right, you understand? And we jog motors a lot, usually to get something in a position before we start it up. So we got, 6 robots over there, and when I get the control of it and I'm manually moving the robot around, we call that jogging the robot, because I'm running the motor. I'm running the motors, right? And I decide how long they run, when I cut them off, when I cut them on, and we refer to that as jogging. And then we have plugging. What's plugging? We've talked about this. Sometimes I think when I plug a motor, what does that mean? Plugging a motor is when we reverse the motor before it comes to a complete stop. And the motor is going to pull start current while it's trying to reverse itself. And a lot of times if we don't size our overloads correctly, then it's going to kick out. And it's not good on the motor, right? Anybody got ceiling fans in their house? You ever go up there and reverse them while they're running? What does the motor do at you while it's trying to reverse itself? So there's just a humming, right? So you can tell that motor's pulling a lot of current. And of course, you're going to decrease the life expectancy of the motor because so plugging, some motors can be plugged, some motors can't be plugged. It basically deals with something we call a service factor that we'll deal with. So this has no we got an anti-plugging switch in here somewhere. I'll have to find it, where it deliberately, we'd have to wire that into the circuit. It does not let you change the direction until the motor stops if you wire it correctly. Are we okay? But this diagram here, this line diagram here, this is right out of the textbook, as far as what is what and where is where. Of course, it adds some more information. It tells us the actual location of the coils and that kind of stuff, which is pretty neat. This is the low voltage transformer. It's a wire for high voltage or low voltage. Yeah, it's wired for high voltage. We hook them in parallel for low voltage and series for high voltage. Contactors have either AC or DC coils, but may switch either AC or DC contacts. Y'all understand that? So the contacts can control a different type of voltage than the coil control, than we use to control the coil. Are you okay there? We already talked about this, about the contacts arcing and that kind of stuff. By the way, the contacts are usually plated with silver, because silver is the best known conductor of electricity, but they're plated. Very, very thin plating on there. And silver oxide with silver rust is as good a conductor as silver. That's very seldom that we see that, but silver has that advantage. So that means you don't, if these contacts look nice and dull, don't try to make them look nice and shiny, right? And don't ever file contacts with a regular file, because if you file them down and you get them down to the copper eats itself up. I mean, it'll eat itself up, and you'll have all types of problems. It'll probably work real nice when you first do it, but after that, we have what we call a burnishing tool that we use. That we can. It's a very, very fine file that we can use to clean the surface of the contacts. This is another little advantage that AC has over DC. AC has the ability to self-extinguish. Okay, so that means we don't have to break the contacts as far apart as we did DC. So DC contacts are going to have to be further apart because DC is not self-extinguishing, right? So once an arc is moving, we create what we call ozone. Ozone has very low resistance. So if we break those contacts, if we break them really slow, this is why contacts have to break extremely fast, that DC is going to try to stay arc, and AC is self-extinguishing because of why? That's right, but it's not the answer I was looking for. What I'm looking for is this right here. Here it goes to 0 volts. If it goes to 0 volts, how much current do we have? 0. So AC has the ability to be self-extinguishing. Now, if you got enough voltage and the ozone don't clear, then, I've seen AC arcs, especially in these big substations, that'll come out and they'll be there for a while because the ozone don't have enough time to dissipate. Ozone pretty much it tries to stay where it's produced. That's why, even though high voltage makes ozone, we can't get it up to the ozone layer, right? Because ozone don't move. It don't rise. It don't fall. It just sits there. So AC contacts can be a lot closer together. We still open them really fast. DC contacts, though, we're going to have to spread them out, and we're going to open them really fast, because when you open something real fast, what happens? Well, you create a vacuum in the center, right? You understand? And when we create that vacuum in the center, we push air through there, and we have the ability to extinguish these things. When we get into these extremely big or high current DC contacts, that is not even enough. So what we do is we create a magnetic field, and we refer to these as blowout coils. First of all, we have what we call arc shoots. Arc shoots means I encapsulate the contacts within a chute. So they're not open to each other. They're within a chute. And just about every one of these relays, you can see the contacts are actually down inside the trough, right? You understand that? Understand. And that's referred to as a chute. So this way, an arc from one contact can't get over to the what? To the other. And we can even go even further than that, where the cap itself, where it comes up there, the cap that sits on top of the relay will actually have chutes through it. And then this sets over the relay, and it basically encloses a contact, so it has no way of getting to so the arc can't get to the other contact. And we refer to these as arc chutes. Okay? And what we're doing with an arc chute is we're isolating each one of the contacts. So when this contact opens, then it's going to suck air through this contact, but any turbulence in this contact is not going to affect the air in the other one, right? So it makes it easier to extinguish the arc if we enclose these contacts within arc chutes. Okay, and this is really a good picture right here. So here's the arc chutes right there. And this is the contacts open, and this is the contacts after the chute has been put on. And the problem we have out in industry is you got these guys, and they'll pull these arc chutes off, and they don't know what they're on there, and then they lose a screw or something, and they leave them off. And then that causes problems too. Also, it helps keep debris out of the contacts too, right? Y'all understand that? In the industry, we have a lot of garbage floating around. Okay, and we're not going to get into magnetism. This is what we call a blowout coil. This is what we use on real high current DC contacts, not on AC contacts, but on DC contacts. And what we do is that we come over here and we so here's where my load would be running. It would be connected to this contact and this contact. But this contact we're trying to break, this is going to come over, and then the load current is going to go through this coil. And when I put voltage to a coil, then I create a magnetic field, right? I showed y'all my little electromagnetic right here. Okay. So this field builds out, but the contact is closed. Okay, y'all understand that? When the contact opens, then the field collapses within this coil. So we set up a magnetic field between these two paddles right here. So here's my electromagnet right here. And then when the coil closes and it opens, and this coil, and then the magnetic field collapses back into this one, it induces a voltage, which just causes the magnetic field to move in the opposite direction. But the magnetic field, when it's collapsing, is flying through the arc, right? You understand? And that is going to blow out the arc. And we call these blowout coils. And these things, when you get into big, heavy current DC, you're going to see these things all over the place. We had one more time where the pedal fell off, one of the pedals fell off. And so as soon as that pedal fell off, then there was no path for the magnetic field to get through the arc. And it was on a crane. Big old DC crane. Big old 40-ton DC crane. And of course, the contact was over just humming at us. And the arc wouldn't extinguish because it was, DC, and DC is constantly doing what? Pushing, right? It's not changing direction. It's constantly pushing. And what did we do? We blew it out. We got there, and we literally had to blow it out. And then we found the plate and put it back on there. But yeah, so we'll run into these blowout coils, and not in AC, because AC is going to try to self-extinguish, even if we put it inside an arc chute. But high current DC, once that thing tries to break, it creates that arc. That arc creates ozone, and then it just keeps going. It just keeps running, right? You understand? Now, we don't have to do this on low current DC contacts because we depend on the contact opening up really fast, and we break it further than the arc can go. Does that make sense? Everybody okay on blowout coils? So if you ever get into some high current DC stuff, especially you go out to U.S. Steel, a lot of your new cranes are running off AC motors because AC motors are so much cheaper than DC motors. The biggest problem we have for years and years is that AC, we couldn't control the speed of the motor. An AC motor wants to run at something below this, but it wants to run at 120 times the frequency divided by the number of poles. So, inside a motor, poles move in tubes, by the way. And then, so if you have a north pole, you have a south pole, and if it's AC, it's swapping directions. Y'all understand that? And so this would be two poles. So if I had a two-pole motor running at, if I had a two-pole motor running at 60 hertz, then the motor is going to try to run at what? It's going to be 120 times the frequency divided by the number of poles, which is 3,600 RPM. And then how would I change the speed of the motor? I've got two ways. One of them is hard to do. One of them is fairly easy. How would I change the speed of most AC motors? So here I've got a motor right here. This is a 3-speed motor. This is a stator for a speed motor. Single phase motor. I got all these wires coming out of them. So what are they doing? They can't change 120. That's a constant. They can't change the frequency because Alabama Power determines the frequency. So how do I change this motor, the speed of this motor? Huh? Somebody said we change the number of poles. And that's why we have a different connection for high speed, low speed, and medium speed, right? You understand that? So what you're doing is you're changing the number of poles. Okay, you're still in thing. You got a little switch, click, 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 and if you took that thing apart, you'd see the switch has 3 wires coming out of it. And every time you click it, what are you doing on your ceiling fan? You're changing the number of poles. Okay, you understand that? Does that make sense now? With DC, to change the speed of a DC motor, we just change the voltage on it. I mean, that's all we have to do. The lower the voltage, the slower the motor runs. The higher the voltage, the higher the motor runs, right? So DC for years has had the capabilities of any time I need to precisely control the speed of a motor, I use DC. And if I don't need to control the speed of the motor, I use AC because AC motors are so much cheaper for horsepower. Everybody follow this? Of course, with electronics, what we have now is we have what we call variable frequency drives. And there's more to it, and we'll try to explain to it a little bit when we look at that. And we got one back there we can see that. But what I can do with that is I can change the frequency. Y'all understand? That makes sense. So a variable frequency drive and the motor is going to be cheaper than a DC drive and a DC motor. So now AC motors are starting to dominate variable frequency drive, speed control. But if you go to work for U.S. Steel is not going to change their 40-ton cranes. If their 40-ton cranes are doing exactly what they want to do, right? They're not going to come in and convert them over from a DC drive over to an AC drive just because the AC drive is cheaper when it's new. It's not cheaper to tear out your DC drive and put an AC drive in, right? You understand? So if you work at U.S. Steel as electronic repairman, you're going to run into these guys. You're going to any heavy industry that's been around for years. You're going to run into these guys because these guys are not going to tear something out that's working to put something in that's new, right? You understand? What are they going to do? What do they want to do? To drop, son. They can't fix it anymore. They're going to run it till they can't fix it anymore, and then they might replace it. Now, when they install something new, it's going to be the newest stuff out there. But so if you go to work, any of these big companies, even like Mercedes, you go to work down there, they've got stuff in there that's been there since the plant opened. Of course, they did replace all their robots for some reason. I don't know. We liked it because they donated all their big FANUC robots to the 2-year college system. So we got 2 big FANUC full big boys, Couldn't fit in this room right here. We got 2 of them on there. This is your contactors. Now, contactors are given a size. So your contactor is what we call the contactors that we're using on our motor starters are size 00s. And then we get over to, okay, what size motor can you run on this thing? So what it says is that, okay, notice as the voltage goes up, the horsepower rating of the motor does what? Goes up. Y'all understand why? So on 230, I can run on a 00 on ours. For 230, I can run a 1.5 horsepower motor. 3-phase. On 460, I can run a 2 horsepower motor. So what changed? Why can't I run a 200 horsepower motor at 460? Huh? If the voltage goes up, what happens? Yeah, because horsepower, what's the horsepower? 1 horsepower is equal to about what? That's another 746 watts. 746 watts per horsepower. Well, what we got is we got I is equal to P over V. That's one of the very important equations that we're trying to learn, right? You understand? So if I've got so what we're saying is if I got a contact that's rated at 9 ounce, that's 9 ounce. Okay? Understand what I'm saying? Well, the higher the voltage rating of the motor, the more horsepower I can run because I'm dealing with 9 ounce. Y'all understand what we're talking about? Yes or no? We okay? I think the size we have over here, that big one I passed around, that's a size 2. So what can I run on a size 2? So the contacts on that thing are rated at 45 amps. So we on single phase, so on single phase I can only run a 3 horse. On low voltage single phase I can run a 3 horsepower. On low voltage high phase I can run a 7 horsepower motor. On 230 volts 3 phase, I can run a 30 horsepower motor. I mean a 15 horsepower motor. So twice the size, but understand the current is being shared by 3 phases, right? You understand what I'm saying? And then for 460, we could run a 20. I don't know what the 330 on that side is. We can run what 25 horsepower motor on a size 2. So on a size 2 motor starter. And those are AC. These are DC contact ratings. NEMA, which is the National Electrical Manufacturers Association, these guys here set a lot of standards for us. Most of the things that NEMA sets are physical standards. The layout of the thing, right? How it's shaped. How do we mount it? Where the mounting screws at? What's the size of it? I understand. So this motor over here has a NEMA frame, a certain NEMA frame. What that means, if I buy a motor that has the same NEMA frame number, it means the motor's going to mount the same, the shaft's going to be a certain size length, right? Y'all understand what we're saying? Because 3-phase, what we have on single phase is that all the current is being shared by these 2 wires. Okay. On 3-phase, we have 3-phase, and the current is being shared over 3 wires. Understand? Yeah. So this current is being shared over 3 wires. That makes sense. On single phase, it's being shared by what? 2. Are we okay? So this is another reason why 3-phase is more efficient than 2-phase. So a 3-phase motor is more efficient for the same horsepower rating than a single-phase motor. One problem we have with a single-phase motor is that all electrical motors work off magnetic fields. You understand that? And of course, like magnetic fields repel each other, unlike magnetic fields do what? Attract. And of course, to induce a voltage, what do we need? We need to have a magnetic field, and we need to have a conductor, and we need to have motion. We understand that. And of course, AC has magnetic field, and AC has motion. Are we okay? You understand that? So if I've got a motor and I've got a 3-phase motor, and then these poles, I'm not drawing all 2 poles. So if this is the north, I've got a pole over there, right? But how does 3-phase go? 3-phase goes like this. Now notice when this guy here starts dropping down, what is this guy over here doing? Okay. So what this does is this automatically, if I wire this, if I call this phase A and I call this phase B, if I call this phase C, then automatically when phase A starts going down, phase B starts building up. And what it does is it makes the magnetic field does what? Shifts. Okay, and then of course when phase B is going down, C is filling up, it causes the magnetic field shift. And then when C is going down, A is building back up, and it causes a magnetic shift. So 3-phase automatically generates what we call a rotating magnetic field. Okay, you understand that? And then the rotor sitting in here, it's nothing but a bunch of conductors. So we induce the voltage into the rotor. So this is one big advantage of AC, is I can get the magnetic field in the rotor, I can induce it into the rotor, right? You understand? I can't do that on a DC motor because DC has all this stuff, but DC don't have what? Motion. Okay. And of course, and what happens if the magnetic field is going out here, it's going into there. So if this is a north, that's going to be a south, right? You understand? Induced into that. And then, of course, when we shift it, everything's just going to shift around. Now, the problem we have with single phase is that single phase has no rotating magnetic field. So when this is a north, this is a south. When this is a south, this is a north. Okay, you understand that? And then what would happen is that when this north, this is a south, that would induce a north. No, this would induce a south. But as soon as this changed, that would be a north. This would be a south. You know, that would be a north, that would be a south. So what would it be? An AC motor can't rotate. And why is that? Okay. We'll go back to this AC motor. I think we've done this before. You know, let's go back to our... Yeah, it says contactor dimensions vary from several inches to several feet in length, and it depends on what they're trying to control. The bigger the contacts are, the bigger the solenoid has to be, right? You understand that's actually doing that. So the size of the contacts determines the size of the solenoid. And then the size of the contacts are determined by what type of voltage they're trying to break and how much current they're going to push through them. That makes sense. Yeah, I saw some relays out of U.S. Steel you just wouldn't believe. I mean, the contacts were as big as you fist. Those things sounded like cannons when they was going off. And so you learn what they were, it would scare you. This is a motor starter with electronic overloads on it. Now, of course, the advantage of electronic overloads is usually they are adjustable, right? So you can actually adjust them here. The biggest disadvantage of electronic overloads is they cost more per overload. So what you'll find out on new installations, you'll probably see a lot of electronic overloads. On installations that's 2 or 3 years old or older, you're going to see heater overloads. Everybody okay there? Different types of overload, circuit breakers, trip indicators. So normally, the reset button doesn't change its position whether the thing's tripped or not tripped. So normally on your overload, you'll have a trip indicator. So usually this one is black. If it's not tripped, it should be red if it is tripped. And that should tell you need to set the overload, right? Everybody okay? This is like your circuit breaker at home. You know, it does indicate when it's popped because it'll pop into the center position, but still it usually has a trip indicator on even circuit breakers at your house. I think we talked about current transformers. Are we okay? Yes or no? This is the nameplate on the motor starter. So let me... So this figure doesn't give us very much information at all. This is all it says is NEMA size 00, and then it says the contacts are rated at 9 amps. But we already know that, right? And the problem with these nameplates, of course, is over time, you know, sometimes they fall off. So this is good to keep the book for. And also, this information is also in the NEC code book inside their motor section. So if you got a code book, I think we get a new code. I think we get a new code next year. Don't get it. Don't code book change in 14. No, it changes in 15. No, 11 was the last one. So yeah, so it does change. So this is the one that we're using. It doesn't give us very much information. This is a Siemens contact. This is not a motor starter. This is a contactor. You understand the difference? It doesn't have overloads on it. So, and then this is the face plate on this thing. And it gives us a lot of information. First of all, in Europe, or anything that's inside the International European Council, IEC, their motors are going to be rated in watts. Our motors are rated in what? Horsepower. So you need to learn the two. So going from watts to horsepower, going from horsepower to watts, then of course I would just take horsepower times, so I take, to get a pretty good idea, I would take horsepower times 746. Now most of your big motors are rated in kilowatts. Okay. In fact, most of the motors are rated in kilowatts. So the actual formula, so I would take horsepower times 746, and then I would divide that by 1,000 to get kilowatts, right? Okay. But books don't teach that. They teach watts equals a horsepower times 0.746. Now what they've done is they've already divided the 746 by 1,000, right? You understand? And your answers are going to be, I should have wrote this. So your answer is going to be in what? Kilowatts. So you can do it both ways. You can take, horsepower times 746 divided by 1,000, or you can take horsepower times 0.746, and that's going to be kilowatts. And why do you need to know this? If you deal with motors, you're going to run into both of them. And eventually, to me, the kilowatts is actually better because it's telling you how much it's going to cost you to run the motor. Over here, we say a 30 horsepower motor. How much is it going to cost you to run that? Right? Understand what I'm saying? So we have to kind of figure it out over time. Of course, if you deal with motors a lot, you have a pretty good idea. But, to start off with. So eventually, the IEC is it's international. The horsepower is basically us. we're the only one using, about the only country still using what we call the English standards of measurement. Even NEC is starting to move over to metric, by the way. Used to, it was all English. Then they put English and put metric in parentheses. But guess what they're doing now? They're putting metric and the English is in parentheses. I know we're very stubborn. They tried to convert us one time, but we said, y'all remember that? So they put up all the mile markers here, and the cars, speedometers had to have both miles per hour and kilometers per hour on there. And we said, yeah. I thought, yeah, it was, I'm picking up that extra camera. So this is basically, this is a NEMA size 1, so I can go back. If I know it's a size 1, then I can come back here and look at a NEMA size 1 contact. If it's AC contacts, then I know in size 1, the contacts are rated at what? 27 amps. And then on 233 phase, I could run a 7.5 horsepower. On the 463 phase, I can run 10 horsepower. And if I use these relays for single phase, by the way, the coils will never be 3-phase. The coils themselves are either going to be DC or they're going to be single phase AC. What we're talking about here is not the rating of the coil, we're talking about the rating of the contacts. Everybody okay there? And contacts that are rated for AC, they don't care if you put single phase or 3-phase. They don't care, because they're just trying to control current for that one phase, right? Or that makes sense? So the type, this would probably give us the frame class, but we're looking over this over here. Are we okay? Any questions? Okay. So what we're going to do is we're going to figure out how to size the overloads. And this procedure is in the book, but what I'm going to do is it's going to be on the next test, but I'm going to give you the procedure. Because this is something where if you did it every day, then you would learn it, right? Here we're going to take a test. We're talking about overloads. So now you have in your mind that I have to go through some procedure to size these things. Okay. This is a manufacturer's overload guide. This is in your textbook. What page is this on? So what we have to understand to do this is we need to kind of visualize the faceplate of a motor. So some of the things the faceplate of the motor tells us is, if I got it in here. I should have it. Darn it. One of the things the faceplate of the motor tells us is it tells us the voltage the motor's rated at, right? If it's rated at multiple voltages, it's going to tell us the two voltages that it's rated at, which in industry you'll run into a lot of dual voltage motors. And of course, the only reason you would wire this low voltage is if high voltage is not available. If high voltage is available, then you're going to run the motor on high voltage. You don't understand why. Because why? Less current to run the motor. The motor doesn't produce more horsepower if you run it on high voltage, right? You understand? It's just going to draw less current to create that horsepower. And of course, you don't pay for current, you don't pay for voltage, you're paying for horsepower, right? Or watts. Are we okay? So that means if I run it for low current, it means I can use smaller conductors to get it out to the motor, and my relay contact can be smaller. So instead of using a size 2, I can use a size 1, right? Are we okay? So what does it say we need to do? So let's find the procedure in the textbook. The procedure in the textbook is hard to understand. They used to give it out really, really nice. So we're working inside Chapter 9 trying to figure out this overload. What page is the procedure on, Rich? Yeah, on page 246. So one of the other things we look at is we look at what we call the full load current. And so when I size the overload, I don't have a really good idea of what the starting current is. I know it's between 6 and 8 times, right? So we size it according to the full load current. And if I size it according to the full load current, the overload is actually designed for that size, is designed to protect you against the start current. That makes sense? So the book on page 246, I look in the right-hand column, and it says check it selection. And then it starts, then it says 1.412, so this is all in here. 1.4 times 1.25 times minus equals 1.8. So it gets kind of cumbersome, right? Y'all see what I'm talking about? Yes? So what we're going to do is we're going to use this procedure right here. The service factor of a motor. Wait, is this one I want to use? The service factor of a motor is how much we can overload the motor for short periods of time. So if I've got a service factor of 1, that means we can't overload that motor at all. Does that make sense? If I've got a service factor of 1.15, what could we overload the motor by? Service factor is a multiplier. That's all it is. It's a multiplier. So if I want to increase something by 110%, a lot of people would come back and multiply it by 0.1, and then they would add that to your original number. I learned a long time ago that instead of doing that, you can multiply it by 1.1. And if you multiply it by 1.1, it automatically gives you the answer what that number would be increased by 10%, right? You understand? Okay. So if I've got a multiplier of 1.25, it means I'm allowing a 25% overload. But to calculate the overload, I can multiply my horsepower or my current by what? 1.25. So on the nameplate of the motor, we have what we call a service factor. That service factor tells how much we can overload that motor for brief periods of time. Okay, does that make sense? Yes or no? And it's usually abbreviated on the nameplate. If you want to grab y'all's motor, that's fine with me, but you can see it on there somewhere. Our service factor on our motor is 1. So here's FF, it says 1. So what does that tell us about that motor? It can't be overloaded. So we can't plug that motor. Because if I plug it, it causes problems with the motor, right? You understand that? Typical overloads for motors are usually 15% or 25%. So a 15% overload would be 1.15, and then a 25% overload means the motor would have a service factor of 1.25. And then that's your multiplier. It's telling you what you need to do, right? You understand? So I'm not changing the current. We're not changing the voltage. We're changing the amount of current, right? You understand? Because the voltage we're applying to the motor is not going to change. What we're doing is we're changing the load. So here, what happens when current goes up? So I can do one of two things. I can multiply the horsepower by 1.15, or I can multiply the current by 1.15. Does that make sense? So I can see how much extra current I would be able to pull, or I could figure out how much extra horsepower the motor could be able to develop. So probably if you got a compressor, that's not right, that's not good. Anything where the load varies, so you have a motor that's running a certain load, and then all of a sudden it's got to do 25 horsepower, and it's a 20 horsepower motor, but it's only got to do that for a short period of time. So it's out here running something, and something else needs to start, right? You understand? Okay. And we start this one, the motor is not going to pull its start current because it's already in motion, but it's going to pull more current until the device gets up to what? Gets up to speed. Does that make sense? Okay. So this is what we're telling us here. It says for 1.15 and 1.25 service factor motors, use 100% of the full load current for the thermal unit. For one service factor, for motors that have a service factor of 1, then you're using 90% of the full load current. Okay, does that make sense? Okay. Then what does it say we do? This don't tell us anything. So let me bring up the procedure. They changed the book, and after this, and they changed this procedure, but this is the procedure I'm going to give you. It's on the test. I'm sure y'all would like to have access to this folder when. Okay, so you can see this is off the test. We're going to give you a nameplate, so we'll go over nameplates. And then over here it says size and overloads. And this is for, now automatically we know that this is after I compensate for either the service factor. So let's assume a service factor of 1.1. I'm sorry, 1.15. What's the first thing it does? Find the overload in the range of the full load current. So let's say I have a motor. Let's see if I can find an example. Let's say it has a full load current of 3 amps. And of course, overloads are not they're not sized for voltage. They're sized for current. How much heat do they produce with that current, right? Oops, sorry. Okay, so what was the first thing I would do? Let's say 3 amps, 3-phase. Okay, so somebody tell me what I do. So 3-phase is going to, so low voltage single phase, I would use this column, right? High voltage single phase, I would use this column right here. 3-phase, I would use this column. Okay, does that make sense? Okay. Now what I'm doing is I'm finding a unit that has an overload where 3 amp falls in there. So what I do, I'll drop down to this guy right here, which is for this manufacturer, that would be B4 overload B4.85. So this number over here on the right hand side, this is unique to this manufacturer. This is their model for this overload. So what did I give y'all? Of course it disappeared. What did I give y'all? 3 amps, 3-phase. So what I do is I come over and look at the 3-phase because I'm going to require 3 units, and I'm dropping down to what? I'm finding where 3 amp falls within that range. And here it is right here. Now, NEC says we can overload the thing because overloads are standard. They're not made for everything, right? NEC says we can size overloads that allow over 125% of their inrush current to go through. And that's even true on circuit breakers. You know, circuit breakers come in standard sizes, right? Y'all understand? So what my load is, 12 amps. Well, there's no such thing as a 12 amp circuit breaker. Okay. So that means, okay, I've either got to go down or I've got to go up. Because circuit breakers are sized according to short circuit, right? You understand? So depending on what we're looking at would depend on whether I'd use a 10 amp or whether I would use a 15 amp breaker. So sizing your breaker is pretty critical. So I'm looking at this guy right here. Everybody okay? Because of what I gave you. I just made it up out of the blue sky. 3 amps, 3-phase. Okay. So that would be my full load current. Where would I get the full load current at? Exactly right, Wilbur. I would get that off the nameplate on the motor. Everybody follow this? Okay. What's the next thing I would do? So I say 3 amps, and then what's the next thing I'm going to do? I'm going to multiply this by 1.25. And what we're doing is we're going to increase that by 125%, which is what NEC allows. Everybody okay? Anybody got their calculator? What does that equal? Okay, well, okay. And then what does it say? Take this and divide it by the full load current. So I'd say 3.75, and I would divide that by 3. What do we come up and get? Okay, we're right on the hairy limits on this one. Now, 1.25. Now, what this says is, it says if the answer is less than 1, then I go to the next overload. I go do what? So this is how much this guy here allows me to overload. That's right at what NEC says we can do. Right? You understand? So this says, okay, we can overload this motor by 125%. If the answer is less than 1, then we choose the next lower, because now we're not even getting 100%, right? You understand? If we have what? If the answer is greater than 1.5, then we choose the next what? So what are we going to do? Okay, if the answer is less than 1, yeah, we got to know. If it's less than 1, then we got to go up. Okay, understand? Because that means I'm not getting 125%. NEC says what? 125%. Y'all understand? Yes or no? Okay. If it's greater than 1.25, it means I've exceeded what NEC says I can do. So that means I have to go. So if it's less than 1, I go to the next higher. If it's greater than 1.25, I go to the what? Next lower. If it's greater than 1.25, that means I'm getting more than what? 125%. Right? Of course, what does ours turn out to be exactly? So this overload right here would be great. Be fine. And this is not nothing. This is not something you have. You just need to understand this procedure because this is the handout for the next test. So what I'm doing, I'm trying to make you learn how to size overloads in this class, but I just want you to know how to follow a procedure to do what? To do it. And of course, if this was your job, sooner or later you'd have this in your head. You wouldn't have to worry about it. But we're not trying to get you to be able to go out here and do this. We're trying to get you the knowledge that okay, I'm going to size these overloads. There's a procedure. I need to look it up. Right? Of course, if you still got the handout from class, what can you do? You can use that. It's just that the way it's set up in the book now, used to the book was so straightforward. But for some reason, when they came out with a new version, they reworded this to make it a little harder to understand. So can we do that? Yes. So let's make sure it's on the chart. So I think this guy here goes all the way up to what's the amps this guy goes up to? This goes up to 18 amps. But that's only on single phase. So let's do something in 3-phase category. Now, normally single phase, you're not going to have to worry about overload. Single phase, single voltage motors. Single voltage motors, you do not size the overload. And why is that? Because the overload is going to be built into the motor. The problem we have with a dual voltage motor is that the current's different for high voltage and low voltage. So a dual voltage motor or a multi-voltage motor, the overloads are going to have to be outside. Because I can't put an overload in here for 240 volts, right, and then wire it and run it on 120. Y'all understand? So a dual voltage motor, the overloads are going to be external. A single voltage motor, 90% of the time, I'm not going to say you're not going to run into one that's got external overloads. But a single voltage motor, the overloads are usually where? Inside. And some of them have a little reset button on them. So you reset the overload. A lot of your smaller motors, the overload is automatically reset if you don't go bad. Like a hairdryer. So your hairdryer has an overload on it. So go up there and stop up the back so air can't get through there and cool that sucker off. And eventually your hairdryer will clip. It'll kick off. But if you let it cool off for a little while, it should come back on because it's got an overload in it, right? You understand? But it's an auto reset overload because you have to reset your. Of course, most of your hairdryers now have to have a ground fault thing. So we're not talking about the ground fault that's on the power plug now that's required on all hairdryers because they're designed to run in damp environments, right? So somebody give me a current. That's somewhere on the chart. Okay, so 5.5. That's a good one because it's kind of, it's probably going to fall in the center. So I'll look at a 5.5 amp motor. Okay, we want it to be 3-phase or single phase. High voltage single phase. Okay, so 3-phase. Okay, number one, and let's say it's got a service factor of, now if it's got a service factor of 1, I would multiply this times 0.9. Okay. If it's above 1, then I'm not going to have to do anything with it. So, Okay, if the service factor is 1, then we're going to multiply the full load current times 0.9. If the surface factor is greater than 1, then we don't do anything. And I'll include that in the, of course, what we're going to deal with is service factor greater. Because most of your industrial motors are going to have and this is also true on the, and then the motor is either rated as continuous duty or intermittent duty. What is it? So a motor that's rated for intermittent duty, it's going to have less copper in it, right? Because it's not designed to run all the time. So if you got an air compressor at home, if you looked at the table if you got access to the motor, it's not all covered up. It's going to be an intermittent duty motor, right? Because air compressor motors don't run all the time. So what that means is they can put extra copper in it, right? Get a lot of extra horsepower out of it, but they only do it for what? For a short time. Then you have what we call continuous duty motors. So somewhere on the nameplate, it's going to tell you if it's an intermittent duty motor or if it's a continuous duty motor. A continuous duty motor means it's supposed to deliver its horsepower for what? 24/7. You can leave that motor running all the time. And it's going to give you a lot of years of service. Of course, eventually it's going to go bad because it's an electromechanical device. In any electromechanical device, you have two things that can fail, right? The mechanic can fail or the what? Just like your car. Your car is an electromechanical device. What usually fails? What fails the most in your car? Mechanics or electric? Use the mechanics. So we're looking at 5.5 amp three-phase service factor of 1.25 or whatever that. So what's the first thing I'm going to do? I'm going to go into the 3-unit column. Then I'm going to look for what? 5.5. So where would I go down to? Looks like I'm going to drop down to way down here right off the bat. B9.10, right? Okay. And then I'm going to take my full load current. So what would that be? 5.5 times 1.25. $6.875, and then I'm going to divide that by the lowest current here, 5.22. No, I'm sorry. Yeah, the minimum overload current, 5.22. Okay, 1.317, that's bad because it's greater than 1.25. So what does this tell us? So it's greater, so I'm going to go lower, right? You understand? So we'd use the B8.2. Not the lowest, we would use the next lower. You probably know what you're saying, but you're saying it wrong. In your mind, you know what you're saying, but when you say we'll choose the lowest, if you say we choose the next lower, then that would be exactly right. Because using this overload, we're going to overload it by at least 137%. And that's why we use the minimum. We don't use the maximum. The minimum is guaranteed. Y'all understand? So anybody got a tack gauge on their car? What's the tack gauge telling you on your car? It's got what we call a red line on it. What is it telling you? So as soon as you go by that red line, is your car going to blow up on you? It's just that it's just not guaranteed to blow up anymore, right? You understand? For overspeed, of course, motors have problems. And that's basically what we're doing here. So we use the minimum because the minimum is what? It's guaranteed. That other guy's not guaranteed. It tells us that it's going to be somewhere between that range. Does that make sense? Yes or no? So that's why when we divide here by 5.22, we don't divide it by the 5.84 because the 5.84 is not guaranteed. This overload is designed to trip at 5.2, but it can go a little above that. So that's why, you know, NEC says we can overload a motor up to 125%. But this is, but it says if you read it, it says if we can't get it, then we can go up a little higher, and that's what the NEC code says. But if this comes up to be less than 1, that means I'm not going to be able to start the motor because now what's going to happen? The overloads are going to click because I can't even get start current anymore. That makes sense. All right, I'm sorry, I can't get run current anymore. And the motor's going to pull its run current if it's running at its rated horsepower. And we try to run a motor at its rated horsepower. And so a lot of people think if I need 30 horsepower work, I can stick a 40 horsepower motor in there. But what happens is the motor becomes a lot less efficient. Its service factor is greater. Not its service factor. Its power factor is greater the further away from its horsepower you run. So that means the motor is you're actually paying for more work than you're getting. 30 horsepower motor, service factor gets up to like, not service factor, the power factor gets up to like 0.85. So the motor's pretty dang efficient, right? Understand? Below its rated horsepower, the power factor gets greater. And the power factor is the ratio between true power and apparent power, right? That's true power over. So everybody okay? So 1.35 is bad. Everybody get this, by the way? I didn't do the math. Everybody get this right here? Okay. It's over 1.35. That's greater than 135%. That means we can't use this overload, so we go to the next lower. If we come up to get a number less than 100, that means I can't. That means we're going to have problems with full up with run current on this thing, right? You understand? So that means I'd have to go to the next tower. Any questions? If I give you the procedure, that's all I can. By the way, this will be on test 2, this will be on test 3, and this right here will be on the final. So, and I'm gonna give you the chart. This is the chart that's right out of the book, right? And then of course I'm gonna give you the nameplate, but I'm not gonna show you this nameplate. So, if you see the nameplate, then you could go ahead and. I do see that this is a continuous duty motor. If I showed you the current, you could go ahead and work this at home. Test 2, of course, all I had to do on test 3 was change the nameplate, right? But this is actually one of the handouts on the test 1. Now let's see what else is on here. On test 2, I'm sorry. Which is when? Next Wednesday. Yeah. Oh my goodness, y'all seen that before? So, and we're going to work on this because we deal with a textbook, but what's this guy right here? This is real life. This is actually off number 4 galvanized U.S. steel. And so the textbook is nice, but when we get here, we see that this is the way it is. Are we okay? Of course, the U.S. Steel don't have manufacturer numbers. So we wouldn't use this. This would help us wire it, but this would let us find it. So the terminal boards. By the way, the problem we get when we get into heavy industry is that all your wires are probably going to be black. So we're definitely depending on what wire numbers to figure out what wire goes where, what relay is what relay, right? You understand? So, and of course, what U.S. Steel does is every terminal you have, which means, of course, we use a lot of stranded wire. What is that? Stranded wire over solid strand wire. Stranded. Y'all understand stranded? So stranded, what we do is we take a lot of small wires and we wrap them together to get the gauge. Solid strand means we have one wire to get the gauge. What's the advantage of stranded over solid? More malleable, yeah, it's easier to move, it's easier to route, it's easier to bend. You know, if these wires right here were solid strands, so yours is just flopping, right? Because they're stranded wires. So stranded wires are more malleable, they're flexible. Solid strand wires are easier to terminate. So to terminate a solid strand wire, we usually just grab our lineman's pliers, put a hook in it, and screw it down, right? You understand? We can't do that with stranded wires because if I put a hook in it and then push it down, all those wires are going, we call it bird cage, and they're going to spread out just like it looks like a bird cage. And if this gets out from under my screw, then those conductors are no longer part of my circuit. And now what I've done is I've changed the gauge of the wire. So if we use stranded wires, it takes more to terminate them. And normally what we do is we have a crimp-on terminal that comes around all four sizes, and we crimp it down on the stranded wire, and then I terminate it with a terminal, right? You understand? And then what they do for those terminals is that's where the wire number will be at, right at the terminal. So you can't find wires getting to it, but you can find wires when they get there, right? Does that make sense? You understand? And of course, why does U.S. Steel companies use the same color wire? You're exactly right. Cheaper. You know, I go up there and I buy a big spool. If I wanted to run red, green, blue, and all these other kinds that we do in residential, then I would have to have different colors for everything. You know, commercial, we usually run multicolor wires. But in residential, we run multicolor wires. Sometimes we re-identify the colors, too. We now get into commercial wiring and residential, especially when we get into cables. You know, if you pull your own wire, if you pull your individual wires, then you determine the color of the jacket, right? Understand? If you buy a cable, then who determines the color of the jacket? The manufacturer of the cable. So when you go out and buy Romax, 14-2 Romax, it's going to be black and white and no jacket. If you buy 12, 12-2 or 12-3, it's going to be what? Black, red, and then either green or it's going to be clear depending on what you run. Glad you could join us. Okay. So plan for next week. We'll have a lecture available. Mr. Sanders, boy, and some of y'all know Mr. Sanders. He's going to cover the class for me next week. And so have a lecture. I'm not going to be here. I'm going to be there. I'm going to be here. We're doing a science, technology, and engineering and math camp, STEM, what we call STEM camps. I'm doing that next week. I don't know if y'all seen these buses here and see a big group of kids moving around. They do like a month of camp, and we each the science department does this, biology does something, drafting does something, and then we do a robotics camp for 1 week. So I'll be over and I'll be here. So if Mr. Sanders runs into any problems, he can give me a call. But he'll do a lecture and then lab. So it'll be kind of like this class, lecture in the morning, lab in the afternoon, and then like the last test, when y'all get here on Wednesday, you'll do what? Lab first and test last. Okay, does that make sense? Second test is going, all our tests are comprehensive. What is it? That's so what does comprehensive mean? From the beginning. Every test is from the beginning. So we just don't test on this. Okay, we go back to the beginning. And what can you do to study the material that was on the first test? You can look at the review. The review's still up there, or you can do what? You can take it again. It's up there. It don't count toward your grade. You can take that as many times as you want to. You can take it for the second test, and then when we take the second test and go over it in class, I'll post it. And when I take the third test, we'll post it, and I'll go over that. And what's the final exam? Yeah, it just comes off the 4 tests. So how are you going to study for the final? Just go out there and take those tests. Yeah, if you can make real high on those tests, you're going to do great on the final. So I can tell right off the bat people do 4 on my finals. Well, not only that's still no excuse, because even if they did part on the other three, they can go up there and take those tests as many times as they want to, right? Of course, the answers are jumbled. So if you try to memorize A, B, C, it's not going to work out. But anyway, okay, gang, I'll take a break and then come back and we'll go in lab.